Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on the periodic table, chemical periodicity. This is topic 9 of the CIE specification, so this is the Cambridge International's specification. So this video is going to go through the topic of chemical periodicity in terms of obviously chemical reactions, period 3, for example. So there's a lot of that information there. So if you're studying the CIE specification, then this is the right place that you need to be to get this information. There's loads of videos. This is obviously just topic 9. There's loads of videos for CIE, specifically for the CIE specification for the full A level. Please subscribe to the Allery Chemistry YouTube channel. It'll have everything on there. That'll be a massive help. All these slides here as well, these are PowerPoint slides, you can purchase them from my test shop. If you click on the link in the description box below, you can get a hold of them there. They're really useful for revision. You can obviously use them alongside your your revision guides and your notes, and you can kind of take them on the move on your phone, tablet, laptop, anything like that. So basically they are really useful, so have a good look there as well. So right, let's crack on then, and let's have a look at the first part of it. Now, and I say this a lot as well, but a lot of the CIE topics are linked with the, a lot of the CIE topics kind of blend into each other. So there's a lot of different topics that kind of interact with other areas of the topic. So other areas of other topics, let me speak clearly. Basically, what I'm saying is, if you haven't seen the other topics, the previous 1 to 8, then I suggest that you look at them first. This kind of heavily links with, there's a lot of stuff to do with bonding, there's a lot of stuff to do with oxidation states in here, there's a lot of stuff to do with obviously the periodic table and trends. So a lot of that stuff has kind of been introduced in previous topics. So if you're not familiar with some of that, then I encourage you to go and watch them first and familiarize yourself with it. I'll try and bridge it as much as I can, of course. So we're going to start with the straightforward stuff first, which is the periodic table. Now, obviously, we know what the periodic table is. We could see it there. Now, in the periodic table, the elements are ordered by proton number, not mass number. So obviously, you're probably aware of that anyway. And obviously, you've got groups which are in columns, and you've got in these groups, the elements in the same group have the same number of electrons in the outer shell. So you would have seen that, like say, from right the way from topic 1 and a bit of topic 2 as well. So the group number relates to the number of electrons in the outer shell. So, for example, group 2 elements have 2 electrons in the outer shell. So this is just a bit of a recap, really. And obviously elements in the same group have similar properties. So, for example, all your group 1 elements react with water with increase in vigor. And you'll see some of them reactions actually later on in this video as we go down the group. So you might have seen these when you put, like, say, lithium and sodium and potassium. So these elements here, when you put them into water, they really react quite violently. Obviously, these ones you wouldn't really have in a lab. These 3 you might do. So lithium, sodium, potassium. Potassium is quite vigorous when it reacts with water. Obviously, the periods are in rows, and we're going to be looking at periodicity. So that's the kind of main point of the topic. And elements in the same period have the same number of electron shells. As you'll kind of see in a moment, we'll look at atomic radius. And obviously, these are what you call S block elements, just as a reminder. These are your P blocks and your D blocks, and finally your F blocks as well. So it's just a bit of a kind of whistle-stop tour around the periodic table. Obviously, this topic is periodicity, so it makes sense to kind of a bit of review of what the different parts are of it. Okay, so let's start with atomic radii then. So radii, obviously we know what a radii is. It's obviously the size of an atom. And as we go across period 3, so this is the 3rd row down, the radius actually decreases as we go across period 3. So we're starting with sodium at one end to chlorine at the other. So if we look at a graph here, we can see that the radius declines over that period. And the reason why is we've got this increased nuclear charge. Okay, so the number of protons in the nucleus of these atoms is increasing. What that's doing is it's pulling in the atom, the size of the atom, a little bit more as we go across the period. So it's kind of pulling all that in, and so the atomic radius is obviously decreasing as we go along. So it pulls them shells in a little bit closer to the nucleus, and crucially, the extra electrons elements they gain across the period go into the same shell. So actually, the shielding effect is no different as we go across that. The electrons being added over that period, obviously the extra electrons in the shells are not going into different shells. So because of that, it effectively pulls the whole radius or the size of the atom in. So make sure you're aware of that. And obviously, atomic radius increases down groups because you got that extra shell of electrons that's been added. So, but in this case, we're really looking at the period side of it, and that's what's going to be quite important. So that's really important. Make sure you can kind of describe that. If they ask you in the exam about atomic radius, it's the increase in number of protons and similar shielding. There's no extra shells being added as we go across the period. Okay. So let's kind of stick with that period, that same period that we've seen there before, and let's kind of examine the melting points of some of these substances. So we're going to look at the first three elements in that period, which is sodium, magnesium, and aluminium. Now these are all metals, so they all have metallic bonding. And I believe this is topic 3, where you look at bonding. There's so many topics, I'm trying to remember what they are. But there was a previous topic on bonding anyway, so you would have seen what metallic bonding is. But if we look at sodium, remember metallic bonding has the metal, the positive metal ions in the middle, and the sea of electrons that kind of coat them metal ions. And it's that attractive force between the positive metal ions and the negative electrons that obviously gives rise to a metallic bond. Now, if we look at the same one for magnesium, you can see obviously we've got 2+ charge instead, with a lot more electrons floating around. Now, obviously what this means is you've got a general increase in the melting point, because obviously you've got an increasing positive charge, you've got more electrons floating around the place, and so this means that you have an increased electrostatic attraction between the electrons and the positive charge, because there's obviously more of them, there's a bigger charge there. So this means that magnesium has got a stronger metallic bond than sodium does, and so therefore the melting point of magnesium is going to be higher as a result, because it takes more energy to break these apart. Okay, so same with aluminium as well. So aluminium is obviously a metal, so it's the same principle. So if we go right to the top, which is silicon. Now silicon has the highest melting point of all the period 3 elements. And it's because it has a giant covalent or macromolecular structure. Okay, so it kind of sticks out like a sore thumb. So this is an example of silicon. Looks very similar to diamond, which you might have seen. So it's got a very strong, very similar structure. Obviously, it's in the same group. Loads of strong covalent bonds hold these silicon atoms together. And so a large amount of energy is required to actually break them apart. And that's why silicon has a really high melting point, because of this macromolecular, this giant structure that it forms. Okay, so let's move on and let's look at phosphorus. And this crashes down to the bottom. It's really low melting point. Now, phosphorus forms this structure P4. It has a lower melting point, much lower melting point than silicon, because it doesn't form these macromolecular structures. It's what we call a simple molecular structure. So they're kind of like mini little pyramids floating around. So the melting point is obviously determined by van der Waals forces here. So you've got much, much weaker forces than what you've had before. And then likewise, if we go on to sulfur, sulfur again is a simple molecular structure, very much like phosphorus. It rises slightly from phosphorus because the molecule is slightly bigger, so it's S8, and because the molecule is a little bit bigger than phosphorus, then it has slightly higher van der Waals forces than phosphorus does. Because it's got higher forces, that means it'll have a higher melting point, so more energy is required to kind of pull these molecules apart. Okay, so if we come on to the last two then, chlorine is smaller still. It has a formula of Cl2. Obviously, it's much smaller than sulfur, so therefore the melting point is lower. And then argon kind of floats around on its own. It's just an individual atom. It's not joined to anything else, so it has even smaller van der Waals forces. And so that's why chlorine and argon have lower melting points than sulfur again. Okay, so the key thing here is about the size of the molecule, and whether you're talking about breaking bonds, which require a lot more energy, or whether you're talking about breaking intermolecular forces, which don't need as much energy. But where you've got obviously phosphorus, sulfur, chlorine, and argon, they all have intermolecular forces between the molecules which need to be broken. The size of the molecule obviously dictates the size of the van der Waals forces that are involved. And obviously that's why we're getting these trends. So make sure you can explain that in the exam. You can talk about the strength of the forces. Don't get it mixed up with bonds. And make sure that you're talking about energy required to overcome these forces. And that's linked with melting point. Okay, so let's look at another property. So obviously that's to do with melting point. Let's look at conductivity. And we're going to look at all of these, again, the same elements, and you're going to find there's a bit of a trend here. We're looking at the same elements and looking at various different elements of chemistry for this. This is all the way through the topic. So let's start with sodium first. So sodium does conduct electricity because it's got that delocalized sea of electrons. Magnesium also does the same. It conducts electricity, and aluminium does as well. So they've all got a delocalized sea of electrons, and that's required for substances to conduct electricity. Silicon is a semiconductor, so it can be used if it's in the right form to be obviously to provide to conduct electricity. So you might have heard of the silicon chip. Phosphorus is an insulator, and so is sulfur and chlorine and argon. So you can see obviously the last four there, they don't have the ability to have any free electrons, delocalized electrons, or form ions in their kind of raw state. So therefore they're insulators of electrical conductivity. Okay, so let's kind of look, we're going to kind of zoom in. A lot of this topic is all about period 3. There's a lot about reactions and zooming in on certain areas of that period. So there's a kind of trend that runs through this topic, but there's a lot of detail. So you've got to kind of bear with us here with this. So, okay, so sodium is in group 1, and it's more reactive than magnesium, which is in group 2. And when they react, they actually lose electrons and they form sodium ions and magnesium 2+ ions, respectively. Okay, so you would have seen that in terms of ionization, which you would have seen in topic 2, I think, earlier on when you look at ionization of elements. So sodium is more reactive than magnesium, as the amount of energy required to remove that electron from sodium is lower than to remove 2 from magnesium, because obviously you need more energy if you're going to remove 2 electrons from magnesium rather than just the 1. So therefore the reactivity of sodium is much stronger. So more energy is required for magnesium to react in the first place. Okay, so it's all to do with removing electrons. Remember, reactions is all to do with removing or accepting electrons. That's a critical point of reactions. So let's look at sodium first. So sodium, as I mentioned before, you might have seen this in the lab where you've got a bit of sodium and you put it in a water trough with probably have a screen in front. You should have a screen in front. And then you put the sodium into the water and it reacts vigorously. It forms a ball and it starts kind of darting around the surface of the water. You get a gas produced, which is hydrogen, and the solution that's left in the water is alkaline, and it's effectively sodium hydroxide because it's reacting with the water. So your reaction is sodium plus water will form sodium hydroxide and hydrogen gas. And obviously you can test the hydrogen gas by putting a lighted splint near it, and you get this nice squeaky pop if it can contain the hydrogen. So magnesium, if you put that into cold water, it doesn't really react that well. It's not exactly exciting. It just kind of sits in the water. So if you react with cold water, it does form a weak alkaline solution of magnesium hydroxide. Now it's a weak alkaline solution because magnesium hydroxide is actually sparingly soluble, so it doesn't really dissolve anyway, the product, and so therefore you don't have many OH- ions floating around in solution, which is important for something being obviously a base, for example, if it's floating around in solution. So here's a reaction here. So this is magnesium reacting with water will form some magnesium hydroxide and hydrogen gas. So very similar to group 1, but just nowhere near as quick. So actually, magnesium reacts a little bit faster with steam, but it forms a different product this time. So you've got to be really careful with that. So instead of forming magnesium hydroxide, it forms magnesium oxide instead. So using steam allows magnesium to react a good bit quicker. Obviously, there's more energy there to allow that reaction to occur. And obviously, here's your reaction here. So magnesium plus water, which is steam, notice the gas state symbol, will form magnesium oxide and water. So just watch out for these state symbols here. Okay. Right, so reactions with oxygen. Okay, reaction with oxygen. So there's here. So your period 3 elements, they will react with oxygen to form oxides. Again, we're going to go back. We're looking at period 3, but reacting it with different substances instead. So the exception is sulfur, which actually forms SO2 that has an oxidation number of +4. You'll see that in a moment. And with a higher temperature and a catalyst, SO3 can be made. Okay, so it depends on how it's actually reacted. So let's start with sodium first. Again, you'll notice there's a lot of similarities here. Sodium reacting with oxygen will form sodium oxide, Na2O. And you get this lovely yellowy orange flame. So when you burn sodium, you get this nice flame. You might have seen it when you did flame tests, perhaps. Magnesium is used in fireworks, actually. You get this really bright white light. You shouldn't look directly at magnesium burning because it can damage your retina. You get it kind of etched into the back of your retina, this kind of burning bit of magnesium. You should always look at magnesium through your peripheral vision and kind of glance at it. So aluminium oxide forms a white product. So when you burn aluminium in oxygen, you get a white powder that's formed. Silicon reacting with oxygen, if you heat it strongly, you'll form silicon dioxide. Phosphorus has a nice yellow flame when you burn it, and you form something called phosphorus pentoxide, which is phosphorus 5 oxide. Now sulfur. Sulfur's lovely because actually when you burn it, you might have you'll normally have like a little spoon that you might burn it in, or you might have it dissolved in solution. But sulfur, or you might just have it on a heat-proof mat. But sulfur, when you burn it, has this lovely blue flame, and you form sulfur dioxide. It's really nice, actually. If you ever get a chance to have a look on YouTube, for example, you might be able to see the burning of sulfur. It's a lovely colour. It's obviously better live, of course, but you know. Right, so just looking at some of the reactions, how quick these reactions are. So obviously with sodium, we produce sodium oxide. It's a really fast reaction, okay, really rigorous. So it doesn't take very much energy. Same with magnesium, it's pretty quick. You put that in a Bunsen burner and it's up. Aluminium is slow. It's not very good. It's better if it's powdered, so you normally use like aluminium powder. Silicon, slow, not very good at all. Phosphorus is spontaneously combust. You've got to be really careful with phosphorus. It's got to be stored correctly because it can just ignite like that. So it's pretty rigorous. And sulfur steadily burns. So you kind of put it in, you get this nice blue flame. Okay, so make sure you're aware of the rates, how fast these reactions go as well. Okay, so let's have a look at the reaction with chlorine. So period 3 elements, they react with chlorine to form chlorides. No surprise there then. So the exception, there's always an exception, isn't there, which is phosphorus, and that forms a mixture of chlorides, and we'll have a look at them in a moment. So let's have a look at the first one. So sodium reacting with chlorine forms sodium chloride. Magnesium reacting with chlorine is magnesium chloride. Aluminium reacting with chlorine is aluminium chloride. Silicon reacting with chlorine will form silicon chloride. Now, phosphorus, you've got two types here. So phosphorus can react with chlorine to form PCl3, which is phosphorus 3. This should be phosphorus 3 chloride, not oxide, sorry. And then you can also form phosphorus 5 as well, so phosphorus 5 chloride. So that should say chloride, not oxide, just to make that really clear. Okay, I'll get that changed. And then sulfur obviously forms disulfur chloride, which is S2Cl2. Just make sure you're aware of these reactions. Some of them are easier than others. Obviously, remember that with phosphorus you get two different types there. And let's just have a look at some of these reactions and what you get. So with sodium chloride, you get this bright orange flame. Obviously, it's orange, so sodium. Bright white flame with magnesium, very similar to when you have it with oxygen. Aluminium has a yellow product, and you get the yellow flame as well. Silicon chloride is colorless, and it's a liquid is formed with silicon chloride. PCl3 or PCl5 is a yellow flame, and S2, so disulfur dichloride, S2Cl2, is an orange liquid is formed. So just make sure you're aware of these colours. It's probably a good idea with things like this is to kind of create little kind of revision cards and make sure you're aware of what they look like and their reactions. There's a lot of different reactions here, of course. Okay, right, so let's have a look at a little bit of structure and bonding. Okay, so looking across the same periods. So the structure and bonding of group 3 oxides. Again, we're still looking at your group 3, or your period 3, sorry, it should be period 3, not group 3. I will get that changed. It affects their melting points as they're plotted on a graph. So let's have a look. So we've got melting points of group 3 oxides, as we've just seen before, and we plotted them on the graph. We're just going to look at a few specific examples here. So let's look at the first 3, which are sodium oxide, magnesium oxide, and aluminium oxide. These all have really high melting points, as you can see on that graph there, as they form giant ionic lattices. Okay, so they form big ionic compounds, and obviously they have really high melting points because it takes a lot of energy to break the strong attractive forces between the ions, and so therefore they have high melting points. So obviously magnesium oxide, this has a higher melting point than sodium oxide, so obviously it's a bit higher up, and that's because magnesium forms the +2 ions. Remember we've seen them before from just pure metal, but it forms +2 ions, and sodium only forms +1 ions. And so the +2 ions are actually attracted much more strongly to the oxygen than sodium is, because you've got a +2 attracted to a -2 for magnesium oxide, and for sodium it's a +1 interacting with a -2. So obviously the bigger opposite, the kind of difference in charge is much bigger with magnesium and oxygen rather than it is with sodium and oxygen. So that means it takes a lot more energy to overcome that force. Now for aluminium oxide, this has a lower melting point than magnesium oxide, and this is a little bit of a quirky one really, but the Al3+ ions, they distort the electron cloud of oxygen, and what this means is there's actually some covalent character there, so it's really pulling the electron cloud that's surrounding the oxygen ion towards itself. And obviously because there's some covalent character in there, it weakens the bond. So your covalent bonding, or the covalent character, is not as strong as the ionic character. So because of the kind of strong 3+, it actually starts to pull some of the electrons towards it, and it's almost like sharing the electrons rather than an electron charge attracting to each other. So it's just that kind of slight quirk with aluminium oxide. Okay, so let's look at silicon dioxide. So silicon dioxide has a higher melting point than the rest of the non-metals of phosphorus and sulfur, as you can see down there. So obviously this has a macromolecular, giant covalent structure, loads of strong covalent bonds that require breaking if you're going to, break it apart and heat it up. So that's going to be obviously really important when we're describing that. Naturally, if we look at phosphorus and then sulfur dioxide at the bottom, these have much lower melting points. As we've seen before, they have simple molecular structures. It's really, we're really looking at intermolecular forces being broken when we're talking about the melting points of these substances here. And because the intermolecular forces, i.e. van der Waals forces, are weaker, or your intermolecular forces are weaker than, say, breaking covalent bonds, then these have lower melting points again. Okay, So let's look at some oxidation numbers. Now, again, you will have seen some of this as well. So this is some of the elements from period 3. They can have different oxidation numbers, obviously depending on what it's bonded to. You should have seen this in topic 6. Now, if you're not comfortable with some of the stuff that I'm going through here, I urge you to go and watch the video on topic 6, because I'm going to assume that you know how to work out the oxidation numbers to actually do this. So what this is really here for in this topic is to kind of link it with, obviously you need to know these, but you need to know kind of the variation in oxidation numbers with some of the period 3 elements. So let's have a look at some here. So we've got the table on the left, and this shows the oxidation numbers in oxides, okay, and the one on the right shows them for chlorides. Now, you are expected to be able to work these out. Obviously, you don't have to remember these. It's about working them out, but you should really look at topic 6. But in a nutshell, or an electron shell, should I say, nutshell, electron shell, whatever you want to say, the elements, they try to attain a stable existence by having a full valence shell of electrons. Okay, that's the key thing. And obviously they'll form bonds with oxides and chlorides to do that, and that's why they actually quite, they kind of react relatively readily, or some of them do anyway. So with some of the elements, you can see there's different ways to actually form them bonds, such as phosphorus. So you've got PCl3 and PCl5, as you can see there. So same element, but they have a different oxidation state. And the same with sulfur as well. When you form oxides, so you've got SO2 and SO3. And obviously these form different oxidation states as well. You are expected to be able to work out the oxidation states in these. Obviously, for the purpose of this topic, you need to be aware that sulfur, when reacting with oxygen, can form 2 types of oxide, and phosphorus, when reacting with chlorine, can form 2 types of chlorides. So just make sure you're aware of that. But the oxidation numbers you should be able to work out. Go back and look at topic 6 if you're not sure. Okay, so let's look at some ionic oxides, and let's have a look at the reactions of some of the period 3 oxides again. But now we're going to take the oxides and react them with different substances. So ionic oxides, we're going to start with sodium and magnesium. Okay, first of all, so that all of these form alkaline solutions when we add them to water. So ionic oxides obviously contain the O2 minus ion. They accept protons from the water molecules when they're dissolved in solution. So you might be aware of this from the acid-base topic that you've seen previously. So sodium oxide dissolves in water quite readily. It forms this alkaline solution, and it forms a pH of 12 and 14, which is obviously a strong alkali. So relatively straightforward. Now, magnesium oxide, on the other hand, doesn't dissolve quite as readily, so it dissolves sparingly in water, and because it doesn't really dissolve very well, the pH isn't as high as if it was say with sodium hydroxide, but the reaction is still the same. So we've got magnesium oxide reacting with water to form your hydroxide there as well. It's just it doesn't form a strong alkali because it's not as soluble. Okay, so let's kind of move further along the period, and let's look at some other oxides of, say, phosphorus and sulfur. We're going to kind of jump into kind of the far end of the table. These actually form acidic solutions when we add them to water. So simple covalent oxides form acids to form solutions with a pH of 0 to 2. So obviously these are strong acids. Obviously this assumes that we have a minimum concentration of 1 mole per dm cubed in 1 molar solution. So let's have a look at some of these here. So we've got phosphorus oxide reacting with your water, and that obviously forms H3PO4, and that's phosphoric acid, which is there. And this phosphoric acid can then dissociate to form your H plus ions. So this is obviously makes it acidic, and some phosphate ions as well in there. So it's kind of this reacts with the water to form that, and then that dissociates to form your protons or your hydroxonium ions, which is H3O plus in reality, and that's what makes it acidic. So just be aware of how that's formed, and then the acid dissociate to form that, because that's what they'll be looking for. Okay, they're always aqueous, remember. Okay, so there we are. So there's your acid that dissociates to form your H plus ions. And then looking at your sulfur ones, again, similar thing. So sulfur dioxide reacting with water to form H2SO3. That H2SO3 can then break down to form two lots of H+. So that's sulfuric acid or sulfurous acid, as it states on there. And there's your example, there's your sulfuric acid there. Okay, so either one of these oxides can react with water to form the acid, and then the acid can then break down to form the H+ ions. It's this which makes it acidic. That's really important. So these are your oxides of that period. So phosphorus and sulfur will form acidic oxides, whereas your magnesium and sodium, they form basic solutions, so alkaline solutions. Okay, so we missed a few out, obviously, in the middle. So we've got silicon and aluminium kind of behave a bit differently when they're added to water. Okay, so let's have a look at these. So silicon dioxide, this forms a giant covalent structure. Obviously, we're aware of that. We've seen that before. And this has loads of strong covalent bonds. It requires loads of energy to break that apart. And silicon dioxide is therefore insoluble in water. So it's sand, effectively. So if you put sand in water, it just doesn't break up, does it? So it will react with a base, though, to form a salt, so it's kind of classed as an acid in that sense, but it's fairly inert. Aluminium oxide is what we call amphoteric. That's a posh word. Basically, it can act as an acid and a base if it wants to, depending on what it's reacting with. So it has both covalent and ionic characters, so it has that mixture of the two. It's a little bit of a hybrid. It's insoluble in water, so it doesn't dissolve. However, it will react with both acid and bases to form salts. So amphoteric is just a name to say that it can act as an acid or a base depending on what it's reacting with, but it is insoluble in water, so it won't actually react with water. Okay, so let's have a look at some acid-base reactions and look at them in a little bit more detail. So your period 3 oxides, these react with acids and bases according to the standard equation of acid plus base gives salt plus water. And you need to know these, okay? So it's really important. So let's have a look at some reactions involving some basic oxides first. So magnesium oxide, we've seen this before. That's reacting with HCl, this is your acid. That'll form your salt plus water, just your standard reactions. And let's have a look at sodium oxide, which is obviously reacting with a different acid this time. For example, this is sulfuric acid. That will form your salt, which is sodium sulfate plus water. Just make sure you're aware of these. Okay, so let's have a look at our acidic oxides. So sodium hydroxide this time is going to react with silicon dioxide. So this is the next one up and across the period. So this is reacting with a base, and this will form sodium silicate, which is this here, plus water. So it's still salt plus water here. Sodium hydroxide reacting with phosphorus oxide. So remember, this is your acidic oxide here. This reacts with the base, and this will form sodium phosphate and water. So you see very similar reactions. Sulfur dioxide obviously is an acidic oxide, so this will react with sodium hydroxide to form sodium sulfate and water. And then you've got SO3, this is sodium sulfate, sorry. SO3 reacting with sodium hydroxide to form sodium sulfate and water. Okay, so all of these reactions, you just need to be aware of them. It's really important. A lot of them is just applying a basic principle of salt plus water. Make sure you're familiar with them. Okay, so looking at amphoteric oxides, so this obviously, or aluminium oxide, which is a little bit weird. It can't decide if it's going to be an acid or a base. So like I say, it depends on what we react it with what it behaves as. So in this example here, aluminium oxide reacting with a base, sodium hydroxide, so this is acting as an acid, will form this compound here. Okay, so sodium aluminium hydroxide. And also, obviously, aluminium oxide acting as a base here, because it's reacting with an acid, will form, obviously, aluminium sulfate, which is here, plus water. So aluminium oxide, Al2O3, can act as an acid, which is here, or a base. So it's amphoteric, as I mentioned before. Okay, so just looking at some final other reactions as well. So looking at chloride compounds reacting with water. So your period 3 chlorides react with water, and their reactivity gives us some information on the type of bonding that's present. So and obviously the types of bonds that's present is dependent on the difference in electronegativity, and you would have seen this in the bonding topic previously. So it's down to how big that difference is. Obviously, the bigger the difference, the more likely it's going to be ionic, and so therefore the bond will be a lot more polar as a result of that. So let's have a look at the series of reactions here. So sodium, which is ionic, has an electronegativity difference of 2.1, so that's the Pauling scale. So sodium chloride dissolves, basically. So if you add sodium chloride into water, then it will form sodium and chloride ions. Very soluble. It is definitely ionic. Now, if we look at the next one, magnesium has a slower difference in electronegativity. Sorry, lower difference, not slower. Lower difference, which is 1.8. So magnesium is obviously ionic. And so this will also dissolve as well. Magnesium chloride will dissolve in water to form Mg2+ and 2Cl-. Okay, electronegativity difference. Aluminium is mainly covalent from what we described before because of the distortion in the electrons of the oxygen. Aluminium kind of really pulls them electrons across, so it does have a little bit more covalent character, even though the electronegativity difference is the same. Now, aluminium chloride, when it reacts with water, actually hydrolyzes. So hydrolyzes just means hydro means water, and lysis means to break. So I think it's a Greek term which means to break, so hydrolysis, so hydrolysis, so hydrolysis. So this hydrolyzes. So basically water breaks the compound down, so it doesn't dissolve, it undergoes hydrolysis. Okay, silicon is the electronegativity difference is much smaller here. So obviously this is obviously 1.2. So this hydrolyzes as well, and this obviously start with silicon chloride, react it with water, and it forms silicon dioxide and HCl. Phosphorus is definitely covalent. Obviously the electronegativity difference is smaller. So this one will also undergoes hydrolysis. So it's PCl3. Phosphorus chloride will form react with 3 molecules of water to form phosphoric acid and hydrochloric acid. And sulfur, the electronegativity difference is even smaller here, so it's definitely covalent, and this hydrolyzes as well, and you've got your reactions there. There is an awful lot of reactions here. However, a lot of them are very similar, and it just follows a pattern. You need to be aware of these reactions and what happens with them. It's quite a tricky topic. There's a lot to remember. Best thing to do is to probably write, say, like little like revision cards, and write down your reactions on them and the kind of properties of them and what you see, and hopefully that should kind of help you to remember them anyway. But what this isn't the case of is remembering loads of equations, although it might look like it on here. There's a theme, and the theme is period 3 elements. That's what they're going to be focusing on. So that's the end of this video. Hopefully it was helpful. Like I say, there's loads of these videos. The full range of A-level videos are available on Allery Chemistry YouTube channel. These slides are also available to purchase. Click on the link in the description box and you'll be able to get a hold of them there. They're really good value for money, and you can use them to supplement your revision. But that's it. I hope that was helpful. Bye bye.